the organizers, other teams, members of the judging panel, and keynote speakers, the audience. Good morning from RO3D-Smart team. We are from Maribor in Slovenia, and it's probably not bad to put us in the context in a way that I can say that we are coming from that part of Europe where you would understand that tomorrow our national soccer team is playing against England at Wembley, and 2 weeks ago we played 1-1 against Chelsea in the European Champions Soccer League. Okay. We are a team of 6 motivated engineers with complementary skills. So Istok is a BIM manager at a company, Lineal from Maribor, the road engineering company. Mojca is a civil engineer playing a role of a IFC researcher here in our team. Clara, civil engineer as well, dealing with road engineering. Sasha is our software engineer, developing algorithms for 3D point clouds. 6th member of our team, Blaž, is a remote sensing specialist. He's not with us. He's responsible for the collection of 3D point clouds. So as this was a shared work this week between the 6 of us, we additionally put us under stress and we decided to give you a shared collaborated presentation, so each of us will actually present his or her part of the work and the participation in the project. So it's about collaboration between complementary skills and engineers. And it's also an interplay or collaboration between different software that we use in this week. And throughout the presentation, so the members of our team will actually present those software and the application of this software. I just want to emphasize that the work plan that we propose or defined for that challenge consists of 7 different tasks, starting with a data collection where we went out to the street and collected 3D points data. Then we continued with the task of actually conceptual design, where we wanted to integrate everything what we did, or to say in a single video that you will see soon. Then we also developed a smart 3D object that we use for road engineering, and we also developed our own software for 3D point cloud analysis and processing that's able to extract features, geometric features of that road. And then we did some reconstruction to that road. So we designed and modeled an additional road to that use case, so that case of 3D points that represents a roundabout in Maribor. We will underline that with our IFC research, so interoperability research, that we also try to rely on throughout our work. So as the next, Istok will present you and comment our video that summarizes actually what we did, and then we'll go into details in the next slide.
Hello. This is a video that we created especially for because we have really limited time for this presentation, for purpose of quick showing what have we done in this week. First, this is a little part of Maribor. I will try to just to add keywords on this video. This is a little part of Maribor. We are focusing on the junction, which is right now somewhere in the middle of the screen. 2 years ago, this junction was a classical junction with traffic lights, and designing of the roundabout has begun 2 years ago, and this year the construction was finished. So we had an opportunity for creating a mobile scan. This is point cloud created with mobile scanning, which we created in Monday. This is 3D model created with smart sub-assemblies in Civil 3D. All the data is represented in InfraWorks. This is video from InfraWorks, but we created this model in Civil 3D with sub-assemblies. This is roundabout laid down to the ground. The next stage was to create a new approach to this roundabout. So first we needed to model a hole, and there was a street lamp in the middle of the road. So this is the two new lamps. And for final stage, new approach, completely modeled with all the data like volumes, materials, and information for 4D and 5D model. So in the next minute we will show details on all of this. Now I think Andrei will tell something about first stage, which is point cloud scanning.
Thank you, Istok. So our next presenter is actually Sasha. He's our software engineer. He will present actually the first of the highlights, which is the software for 3D point cloud analysis.
Thank you, Andrei. So I was responsible for the development of software for point cloud processing. Here we can see the car with which we obtain the data. On the car is a LiDAR technology mounted that scans the street or the roundabout that we actually work around. So LiDAR stands for light and detection and ranging. It's a remote sensing technology that uses light to detect features of distant objects. It measures the two-way travel time of emitted laser pulse, laser beam, and the recognition of its reflection. So we programmed our software that we see in this picture in C++ language in the Visual Studio environment. Here we can also see the point cloud data that we obtained. We visualize here around 6 million points that we then slice it like a cake and present it in cross section. So if you look here, we can see one of these slices. This is actually the cross section where we can also define the thickness of this cross section. It's predefined with 5 centimeters of thickness, but we can change that manually. One of the features of this program. The cross section points drawn here are like 4,000 points. That's way too many for this recognition. So we tried to eliminate some redundant points. Sorry for. Okay. So we remove points that are collinear. That means that the points that are in a line are removed, and points that are doubled. It means that points that are that have the same x value are also removed. So in this way we are able to reduce points up to the half. So we had around 2,000, 2,500 points. And out of these points, we then recognize so-called dominant points that represent the road elements. So we tried to find curbs, gutters, and roadways. These points are then combined to brake lines, and they are exported with a land XML. Thank you.
So, I will just continue with that second part here. So the land XML file is then actually exported with our software, and you can see it on the slide, into the Civil 3D. So this is the surface generated out from that Civil 3D imported file. And we use that actually in the further process so that road engineer can actually attach to the feature lines of that surfaces and further model, so continue with the engineering process. This is part of the code, so the most important one where you can see what actually Sasho explained. So the most vital part of our software. A couple of words about the research that's actually behind. So we had to research into a lot of literature, scientific one, and we started with a so-called, so the problem of how to fit actually a 2D line into that cloud point. So, but this was actually a wrong approach. There is one of the famous algorithms here is known as a Ransack algorithm. It's actually a very old, more than 20 years old algorithm that has actually been improved over the years and still under active development. Then the next step was actually how to extract the arcs and lines from that point cloud. This was also not the perfect direction of our research. Then we ended up actually with more mathematics, so to say. So it was approached from the field of discrete geometry, and combined with, of course, computational geometry, when we used the notion of so-called fuzzy segments or blurred segments that result in that final dominant points detection. And we're happy to say that it's actually an algorithm that produces those dominant points in a linear time. So it's no exponential, no logarithmic time complexity, but it's a linear time complexity. So now Isok will continue with the smart object, so the next highlight.
Thank you. In order to start with smart objects, I need to maybe go a little back in time. The traditional way of road design for now, or maybe for before a few years ago, was so that the designer has created basic geometry and then just manually drawn cross sections through each section line. This was a problem that we wanted to solve. We did that with sub-assembly composer from Autodesk in combination with Civil 3D. Here you can see situation. Top right there is a cross section of the model, and bottom right there is a 3D model representing that roundabout. This is created with we call it smart objects. It's a parametric design which works something like smart decisioning of cases that we gave to the model. So that means we just gave we are giving parameters to the model about desired geometry. Then we show them on which surfaces he should look. And with that information, the model automatically decides which solution will be right for model. This is only an example how parameters are inputted inside in Civil 3D, and the next stage is how additional parameters are inputted, like surfaces or alignments, edges of road or anything. In bottom right, you see a picture from our video. The models that are created with that kind of work are automatically created when designing a road. So that means that the designer doesn't need to have a modeler after him in order to have a quick visualization, all the data about volumes, masses, materials, and that means that all the informations are there for 4D and 5D design. Currently this is the list of the sub-assemblies. I can say that we can create one complete road with this list of sub-assemblies, and of course with the last one that we created this week, which is specially designed for roundabout. Maybe Clara, next slide, it's about how we modeled this roundabout and the new approach.
Thank you. How we implemented 3D smart objects to engineering route modeling of this roundabout and new approach to roundabout. So at first, just some basic information. The roundabout radius is 18 meters, the line width is 5.5 meters, and the track around 2 meters. So what we need to model a route, we need at first the alignments. You can see on the pictures existing alignments and the route about alignment that we created, and this alignment for a new approach. Of course, we have to be aware that these alignments are all 3D lines. Then we need the profile view and the surface profile view, of course. Which sub-assemblies we used to model that roundabout and the new approach. Of course, our main idea of modeling is that we have to use the basic sub-assembly that is on this top picture. It's just two lines, but are meaningful for the design because of this corridor. With this sub-assembly, we create the bottom surface, which will represent the surface target for other complex sub-assemblies that we will use further. So we use basic, as I mentioned, and for a roundabout we use a roundabout sub-assembly that we developed in these few days. And for a new approach and edges of a roundabout, we use roadway and gutter sub-assemblies that we already have before. So, I will explain now the idea. At first we use this basic sub-assembly with two lines. We create then the bottom surface from that corridor, which is the surface of a road construction that some assemblies will be attached to. And in the picture below, we see the basic corridor made for a roundabout. So now I will tell something about the approach. Of course, we have alignment, the profile view, that bottom surface. Of course, with the parameters were set to different numbers for this approach because the geometry were different as for roundabout. Then we used sub-assemblies. And with these sub-assemblies, we build the corridor. Corridor represents the 3D model of a road. So we use the roadway. This is the line of a road, and the gutter with the berm on one side of a road, and on the other side of this approach, we use a gutter with a curve. So we built this corridor in marked blue. From this corridor, we export solids. We have to be aware that these solids all have layers, material properties, and geometric properties. And then we convert these solids to a mass element, And with that masses, we can take off the quantifications. So if we export these to Navisworks, you can see with the red circle, it's a mass element that is marked in the image. And then we can see on the right side the properties. This mass has volume and the height and the weight properties, parameters. And of course, if we have all these, we can calculate the costs of these models. So this is not just animation, but we can say the model.
And the main task of our BIM and RC research was to determine which export file format we have to use in our point cloud algorithm. We decided on land XML because if we use land XML in Civil 3D, then we can create 3D digital models which contain just a second. Okay. Excuse me. Says we can create then models in which the elements have. The elements have the geometry, mass, and material properties. And the second point, the level of change integration is actually incorporated in the smart object. That means that the changes are instrumentally working through around. If you make a change in subassembly, it's shown in assembly, and if the assembly is changed, then the corridor is changed as well. We are not using 2D reference files to create a model, but it's in one file with 3D elements. And the last point, all the changes that are made are automatically updated in all corresponding views and animals. And as you can see, our 3D digital model is not a non-BIM model, according to Professor Chuck Eastman. So we can actually say that we created a BIM model or a semi-BIM model. This is the label must be set by the experts which are here today. Additionally, we tested the Open Infra viewer. It's a land XML viewer developed by the Technical University of Munich. And as you can see, we imported the data of the corridor and the land XML surface, which was created from the point cloud. And as you can see, the data is already shown correctly. So if we applied some additional data, like material or the cost or the construction manufacturer or something like that, we can actually achieve BIM using this extended viewer. But this viewer is actually meant for the IFC viewer, not just land XML. So we did some research and we found that the IFC bridge is at the moment under the construction and development. And as you can see, the reference lines that are used for bridge modeling can also be used as a road reference lines, or as better put it, the reference curve of a bridge is the same as the reference curve of a road. So if the IFC for road is being under development and it's almost finished, we can say that the IFC for roads, it's on the same way. It's going to take a few more billion of dollars and some man-labor hours to develop that, but we can say that our approach with using land XML and Civil 3D is the basis on which the IFC road can be developed and then used. So the switch from the DVG 3D files containing the properties of mass, geometry, and material can then be easily applied to IFC. There's not going to be needing any changes and so on. So this is our next step of our development after the CITA 2014 challenge. So maybe in 2015 we'll come here and show you more of the IFC road, some elements and some of our propositions.
I just want to conclude our presentation with a final slide. So just a few lessons learned and the future directions for our work. So the most invaluable experience was joint collaborated work. So we spent more time together as we spent with our families. Then from the scientific research point of view is that the next step would be actually to step a bit one level up and say that we want to create semantic objects from the pure geometry objects from that 3D point cloud. And of course, this can be used for a variety of purposes. So smart road, for example, can detect damages on the road. So this can also be done with the further development of our software. We're also planning to join the Open Infra initiative. So the guys from Munich and the France that do that IFC extension. So Thomas Liebig and other researchers. So, and I will conclude our presentation with a more engineering statistic. So I started with a sports one. I just want to say that Slovenia is, according to the latest statistics, a top EU country in terms of because we have 40,000 kilometers of roads, and that makes us to the top of the European countries in terms of size of our country. So thank you very much.
What I'm going to do is just take one or two questions. If somebody has any questions.
Brian Fair from the DIT. Following on from Ralph's question about being up to speed on coding, you lost me at some stages at the level of technical detail. Within the collaboration, were all of you reasonably comfortable with the level of coding, or was there a knowledge sharing that had to happen within the team to make it successful?
Okay, I can say, so Sasha is our software engineer. The initial code base that, so it's not a coincidence that he's with us, okay? It's part of his research, actually. He has a basic code base. He provided us with a basic code base when it comes to Visual Studio development and the manipulation of, the presentation of the video point cloud. So the really new thing is that algorithm. So we indeed developed it in that time. So it's not perfect, okay, as I said, but we, as you can notice, those who approached us last night, we still were testing and debugging our software, but at midnight we managed to actually put that image into one of our slides. Yes.
This process of developing the algorithm was actually a collaborative work, because Sasha needed the information from me about which export files to use, and I had to do the BIM research, which files are the most manipulative, which have the most properties in them, and then I had to collaborate with Iskok, which is a road designer specialist, because we needed to know which are those feature lines that are needed, which data is actually the most important one, so that our algorithm is going to work on a very precise way. So actually it was like a collaborative space. Andrea and Sasha were developing the code and then testing with us what are our needs to be fulfilled. So it was actually a joint venture, and we did like a startup approach. So everybody did their work, and then we shared our knowledge, because if just Sasha is going to develop the algorithm, he doesn't know what he needs. So we did something like that. I think that's the question.
And you also have to understand that my basic education is also software engineering.
Any other questions? Or can I congratulate you and your team on a good presentation? Well done.